Greetings everybody and welcome back to another exam video. Today we're taking a look at the 2023 Methods Exam 1. They just finished their methods exam, so I just got my hands on this from one of my students. So if you're watching this, you know who you are. You're an absolute legend. Yeah, this is actually my second time recording this because first time, guess what? The audio absolutely messed up, so it's kind of unusable. But this is nice though because I kind of paused a few times in the first recording, so hopefully this recording is a bit more fluid. Yeah, let's just jump straight into it and see how we go. So question 1. Nice derivative question, so let's quotient rule this. So do we have dy on dx? That's just equal to, we have, if we call this a v and we call this a u, it's going to be v, which is e to the x, times u dash, which is 2x minus 1. And then we have minus u, which is x squared minus x, times v dash, which is e to the x, divided by the bottom squared, so v squared, so that's e to the x times e to the x. I'll just write it like this, and then notice that we can cancel a bunch of stuff. So we have cancel, 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 and what are we left with? We are left with something over e to the x. And what is that something? Well, we can probably think about this over here. We have 2x, we have minus 1, we have a minus x squared, and then we have a double negative, so a positive x. So what we end up with is a 3x, and then we have a, let's write it as negative x squared plus 3x and then minus 1. And that's our derivative. Okay, let's f of x equals this product thing over here. We want to find f prime of pi and 4. So how does f prime look? So f prime of x is equal to, we differentiate the first guy, keep the second guy, and then plus, keep the first guy, differentiate the second guy, which is 2e to the 2x. And we want to plug in pi and 4, but before we do that, I'm going to factor out e to the 2x just so there's less places for us to plug in pi and 4. So cosine of x, and then we have plus 2 times the sine of x. Okay, plugging in pi and 4, what do we get? We get f prime of pi and 4 is equal to e to the pi and 4, pi and 2, because 2 times pi and 4 is pi and 2. Cosine of pi and 4, that's square root of 2 over 2, plus 2 sine of pi and 4 is also square root of 2 over 2. And what's this stuff over here? That's just 3 halves square root of 2 over 2, I think, because 2 and 2 will cancel. Alright, so you have 1 lots of square root of 2 plus another half of square root of 2, which is 3 halves of a square root of 2. So there's 3 halves square root of 2, e to the pi on 2. So that's f prime of pi and 4. Let's take a look at question 2. Question 2, we have this equation here we need to solve. So here we can just turn this into a quadratic. Let's bring everything over to the left hand side. So e to the 2x minus 4 e to the x and then minus 12 equals 0. Okay, and to turn this into quadratic, we can just think about this as e to the x but squared minus 4 e to the x and then minus 12. So this is basically a quadratic in e to the x. So e to the x is kind of like a variable in this case. So applying the quadratic formula, we get e to the x is equal to, we have a minus b, which is 4 in this case, plus or minus the square root of b squared, which is 16, negative 4 squared is 16, minus 4 times a times c, which is negative 12. And this is all divided through by 2 times a, which is 2. So this is a 4 plus or minus square root, 16, and then we have a plus, what's 4 times b squared minus 4ac. So this is a 4 times 12. What's that going to be? That's 48, I think. And then you have a 16, so that's going to be like 64. And then this is divided by 2. Okay, let me just check that. 4 times 12 is 48, right? And then plus 16, that should be 64. Okay, so this is 4 plus or minus 8 divided by 2. And this is, we have 2 plus or minus 4. So e to the x is either going to be equal to, we have 6 for the plus solution or negative 2 for the negative solution. But we can't have the negative solution because e to the x is never a negative number. So if you apply logs on both sides now, so yeah, going all the way up over here, we have finally x is equal to just log base e of exactly 6. Of course, yeah, log base e of negative 2 won't make sense. It's imaginary, but we're not doing imaginary numbers. Okay, question 3. We want to graph this hyperbola, labeling asymptotes with their equations and axial intercepts with their coordinates. So what are the asymptotes? Well, that's very easy. It's x equals 1 over here, and it's also x equals 2. So right over here. So this is x equals 1 and y equals 2. Okay, yeah, that should be pretty straightforward. Let's try to find the axial intercept so we know how to graph it. So let's do y-intercept first. That's simple. So plugging in x equals 0, we get y equals 2 minus 3 over negative 1, which is, yeah, just 5. So we're up over here. Let's do the x-intercept. So the x-intercept's just setting f of x equals 0. We get 0 equals 2 minus 3 over x minus 1. Bring it over, we have 3 over x minus 1 equals 2. Let's separate over here so we don't get confused. So bringing the x minus 1 over, we get 3 equals 2, x minus 1. So 3 on 2 equals x minus 1. So adding 1 on both sides, we get x equals 5 halves. Okay, so x equals 5 halves. So that's going to be the x-intercept, which is right over here. Okay, and yeah. In my first recording, we figured out that it passes through this point as well because of the next question. So I'll just put it in so I can actually just graph the thing right away. Okay, so we get a graph that looks something like this over here. There's no domain restriction, so yeah, we can just graph the whole thing. So next we want to find the values of x for which f of x is less than or equal to 1. So f of x is the y value, so we want to get everything that's below 1 over here. So we want everything over here. And where exactly does that occur? It occurs when we're over here on the graph, right? When we're below negative 1. So we're going to be greater than 1, strictly greater than 1. And whatever this point over here, which, well, I've given you the value is 4, but let's actually just find that and pretend we don't know this point exists. So how do you do that? You can just let f of x be equal to 1. So what does that mean? It means, what is f of x? F of x is like 2 minus 3 over x minus 1. So 2 minus 3 over x minus 1, that's equal to 1. So what does that mean over there? It means that's, let's bring the 3 over x minus 1 over to the other side and bring this one to the left hand side. That gives us 1 is equal to 3 over x minus 1. So that means that's x minus 1 is equal to 3, which means that's x equals 4, which is the point we got over here. So when x equals 4, the value of f of x is exactly 1. So because we want all the values that are less than y equals 1, we're going to take x to be greater than 1 because of the asymptote, and also 4 strictly, no, not strictly, less than or equal to 4. So those are the values of x there. Okay, so that's question 3. Question 4. Let's see. We have a trapezium rule over here, so we have a funny graph, x plus 1 over x. So we want to find the area, or approximate the area between the curve and the x-axis and the lines x equals 1 and x equals 3. So right over here, using two trapeziums of equal width, because it's 2 and the distance over here is exactly 2, that means the width is exactly 1. So we want to find the function values over here, and we want to connect these with lines like so. Okay, so we can just use the trapezium formula, or the trapezium rule formula, whatever it's called. So area is equal to the width over 2. So what's the width? It's 1. So 1 over here, that's the width. Okay, and we divide this by 2, and then we have a bracket, and then what you do is you take a look at f of the first endpoint, f of the last endpoint, and they're just as they are, and then everything in the middle you do twice of, so 2 times f of 2. There's only one point in the middle, which is x equals 2, so you only do one of those. And that's it. Really what we should do is we should let f of x be equal to x plus 1 over x as well, because f of x wasn't defined in the question. Okay, so let's just carry out this computation. Shouldn't be too bad to do. So this is 1/2. We have f of 1. So what happens if you plug 1 in over here? You have, let's see, that's 1 plus 1 over 1, which is 2. So 2, and then plus 2 times. We have 2 times something. What's f of 2? F of 2 is 2 plus 1/2. 2 plus 1/2 is 5 halves. So this is 5 on 2. Then plus, what's f of 3? It's 3 plus 1/3, so I'll just write this as 3 plus 1/3, like so. Close bracket. That's all of it. So this is 1/2. We have 2's are going to cancel, leaving us with 2 plus 5 plus 3 plus 1/3. What's 2 plus 5 plus 3? It's 10, I think. Yeah, 10. And then we have plus 1/3. And this is going to give us 1/2. And then what's 10 as a fraction? It's 30 over 10. No, 30 over 3. 30 over 3 is 10. And then plus 1/3. And this is equal to 31 over 3. And then we have division by 2 over here. So that's going to be 31 over 6. I think that's the answer I got before. Hopefully that's right. Question 5. We have a nice integral question. It's just the integral of sine. Good job, VCAA. So how do you evaluate this? This is negative cosine of x, which is the integral of sine, evaluate from 0 to pi on 3. You can bring the negative out if you want to, so negative. And then we want to evaluate cosine of pi on 3, which is 1/2 if you think about it for long enough. And then you have a minus cosine of 0, which is 1, like so. And this is just going to be equal to 1/2, because a half minus 1 is negative a half, and you got the extra negative out over here. Okay, so we know the integral is 1, and then we want to use this to find the values of k, such that the integral that we literally just did in part A, which is 1/2, is equal to some other integral over here, right? So probably the best way to do this is just to evaluate this integral with the parameter k in it, find some kinds of value for the area in terms of k, and then just equate it to 1/2. And maybe get like a trig equation or something. So doing so, let's just think of, let's just write it like this. So we have 1/2 is equal to the integral from k to pi on 2 of cosine of x dx. And this is equal to, we have, let's see, negative, cosine integrates up to sine. The sine of x from k to pi on 2. Okay, and this is just going to be equal to sine of pi on 2, and then minus sine of k. That should be everything. Okay, so what's sine of pi on 2? That's just exactly 1. So rearranging the whole equation here, we get sine of k being equal to 1/2. Okay, and let's just solve this now. So what are the possible values of k? Well, if you think about the unit circles, here's the unit circle over here. If k is the angle, how do we get k equal to 1/2? Well, we could be, well, here's the line y equals 1/2 over here. We could be at this position or this position. Okay, so what are the values of k? We can get k equals, this position over here would be pi on 6. And we also got, that's going to be 5 pi on 6 as well. 5 pi on 6. And yeah, we're only allowed to go up to 2 pi. So that's all the solutions up to 2 pi. Can we go backwards though, is the question. And yes, we can, because if you start at 0 over here and start walking backwards along the unit circle, you actually get back to this position over here, which is negative 7 pi and 6. Negative 7 pi and 6. And it can keep walking around as well. And this position would be negative 11 pi and 6. Right? And then I don't believe you can keep going any further, because once you do a full revolution backwards, you're already at 2 pi. And we're only allowed to go to negative 3 pi. So negative 3 pi would be an extra half revolution here. And you're not going to pick up any more solutions with another half revolution. So I believe these should be, these should be all the solutions. For part B. Okay. So question 5, not too bad. Question 6, we have sample proportions. This one's quite nice. So we have a 95% confidence interval over here, and we want to find the value of p hats. Nice and simple. P hat's always the average of the endpoints. So what's 0.04 plus 0.16 divided by 2? That's 0.2 divided by 2, which is 0.1. So p hats is 0.1. Using z equals 2 to approximate the 95% confidence interval, we want to find the sample size from which this 95% confidence interval was obtained. Okay, so I think in the first time I record this, I tried to use decimals and that didn't work out well, so I switched to fractions, which is a lot nicer. And knowing that, I'm going to use fractions from the get-go, just to avoid the pain and confusion. So what's the margin of error formula? It's equal to the z-score times the standard deviation. So p hats 1 minus p hats divided by n, like so. We use this because it has the n over here, which we can use to solve for the sample size. Okay, so what's the margin of error? It's distance from the p hats to one of the endpoints, so that's just going to be 0.06, and that's going to be 2, because that's the approximation for the z-score, and we have the square root of p hats, which is 0.1, but let's write this as 1/10 times 9/10, which is 1 minus p hats, and this is divided by n. And instead of writing 0.06, I'm going to write 6 over 100. Okay, so let's rearrange things a little bit. So this is bringing the 2 over, we're going to get 3 over 100. Bringing the square root over, this whole thing is going to be squared, and this is equal to 9 over 100. And then we also have an n in the denominator as well. Okay, and we just got to solve for n from here. So let's see, if we expand out that squared there, we're going to get 3 squared, which is 9, over 100 squared. We can cancel the 9s on both sides, and we can cancel a factor of 100 on both sides, so that gets rid of this 2 here. And what does that leave us with? It leaves us with 1 over 100 being equal to 1 over n. But that means n is equal to 100. So don't use decimals, otherwise you have to count decimal places, which is annoying. Okay, a larger sample of household is selected with the sample size 4 times the original sample. The sample proportion stays the same. By what factor will the increased sample size affect the width of the confidence interval? So it's actually going to half. Maybe you've seen these type of questions before and you know what the answer is straight away. How can you see this? Well, what's the original margin of error? M. It's equal to z, square root of p hat 1 minus p hat divided by n, right? And now with our new margin of error, so let's just call it m twiddle, is equal to, everything stays the same, so z-score stays the same because it's still a 95% confidence interval. We have a square root of p hat stays the same as well, 1 minus p hat, but n changes to 4 times the amount. So this is 4n over here. Now what you can do is you can factor that 4 out of the square root, and what you get is 1/2, not 1 over z, 1/2 z square root of p hat 1 minus p hat divided by n, right? But notice this part over here is precisely your original margin of error. So this is 1/2 times m. So your new margin of error is exactly a half your margin of error, but because the length of the confidence interval is exactly twice the margin of error, the length of the confidence interval also decreases by a factor of 2, or increase whatever. It just halves pretty much. That's question 6 there. Nice and neat question. Okay, question 7. So down to the business end of the exam now. So we have a function which is a quadratic. It's defined on the interval negative infinity to 1. State the range of f. Well, that's very simple. Look at the graph and we see y is on the interval -1 to infinity. I got that completely wrong. It's -1 to infinity, not 1 to infinity. Because it starts down over here and our function starts at -infinity, so we're just going to shoot up forever. Right, so that's the range, nice and simple. 1 mark. Sketch the graph of the inverse on the axes above. So how can you get the inverse? Well, we'll just map all the points over and flip the x and y coordinates. So we have the endpoints over here, which is at -1, 1. So the inverse will have its endpoints at -1, 1 instead. We cross through the origin, which means the inverse will also cross through the origin, and we can get another guide point over here. So you know the function passes through -1, 3, which means the inverse passes through 3, -1. So right over here, and we just got to connect the dots. So something like that's probably, guys could probably do a better graph than me because I'm doing this on a drawing pad and it's not too easy to graph this nice smooth lines, but that's good enough. Okay, so we've graphed it. We also need to label endpoints and axial intercepts. So I mean, there's only one intercept over here, 0, 0, and the endpoint is at -1, not 3, -1, 1. Perfect. So determine the equation and the domain of the inverse function f inverse. So we just got to take our original function, replace f with y, switch x and y around, and then solve for y once again. So doing so we start off with y equals x squared minus, was it 2x? X squared minus 2x, was it? X squared minus 2x. And we're going to switch the x's and y's around. So we get x is equal to y squared minus 2y. So what does this tell us? It tells us that x is equal to, we really want y in one place, so we can actually rearrange things. So how do we get y in one place? Well, I'll complete the square. So we get y minus 1 squared minus 1. That should work because this expands to y squared minus 2y plus 1. And then we have a -1 just to get rid of that extra plus 1 there. And, well, we just rearrange for y now. So this is x plus 1 is equal to y minus 1 but squared. But this tells us that if you take the square root on both sides, we get y minus 1 is equal to plus or minus the square root of x plus 1. Question is it plus or minus? Well, choosing plus or minus will determine the range of the inverse, but remember the range of the inverse is the domain of the function. What's the domain of the function? It's negative infinity to 1. So we kind of want the range of this guy to also be negative infinity to 1. Actually, it has to be negative infinity to 1. So it doesn't make sense for us to choose the positive branch over here because we'll get like something going from 1 to infinity. So we've got to choose the negative branch. So y minus 1 is equal to negative square root of x plus 1. And yeah, bring it up over here. We have y is equal to 1 minus square root of x plus 1. And remember to replace it with f inverse of x. You will probably lose marks if you don't. And yeah, that should be it over there. All right, and you can kind of just do a sanity check as well. The square root is, the range of a square root is from 0 to infinity. You put a negative in front, so it goes from negative infinity to 0 now, and you add 1 to everything, so it's going to go from negative infinity up to 1. So that matches with the domain of the original function. So yeah, happy days. Okay, and I think there was an extra part as well. Yeah, find the area enclosed by the regions of f inverse, and y equals negative x. So let's think about what that region is on this graph. I don't think it's a good idea to draw it on the original graph. Maybe you have to draw a separate graph if you want to visualize it, but I'll do it here because I'm lazy. So here's the line y equals negative x, like so. And the area enclosed is this little, slither over here, these two slithers. So how can you calculate the area of this thing? Well, using the symmetry of the function and its inverse, these two areas are actually the exact same thing because they're just mirror copies of each other. So it suffices just to find one of these areas, and I'm going to choose the area bounded by negative x and the original function, which is a quadratic, just so I don't have to integrate as square roots. Right, so we know that the area we're after, let's call it A, the area is equal to twice the integral of something. What's the integral? Well, let's look at this over here. It's the integral from 0 up to 1 of top function minus bottom function. What's the top function? It's negative x. What's the bottom function? That's x squared minus 2x. Yeah, x squared minus 2x. So it's the integral, and we go from 0 to 1, top function minus bottom function dx. And yeah, just got to evaluate this now. We can probably simplify it actually. So this is 2 integral from 0 to 1 of negative x squared, and then we have minus x plus 2x. So what's minus x plus 2x? I think it's plus x dx. And let's just evaluate this integral. Nice and simple. So this is equal to 2. This is 1/3. We have an x cubed, and then plus a half, and then we have an x squared from 0 to 1. We can ignore the 0 because plugging 0 in, that's gonna make everything 0. So if we just plug 1 in, well, what do we get? We get, this is 2, and then negative 1/3 plus 1/2, and that's 2. We have negative 1/3 plus 1/2. I think that's like, let's just calculate it. So this is negative 2, I can't do fractions. What's a third? That's 2/6. And then we have plus 3/6, and that's 2 times 1/6. Right, so that's 1/3. I think that's right. So negative 2 plus 3 is 1 over 6. Yeah, that should be right. So the answer is 1/3. Okay. Moving on. So that was question 7, I think. Question 8, and this was a bit of a cooked question. Took me a while to get through this one. Okay, so we want to show that k equals 1/64. So we just got to integrate this density and set it equal to 1. So 1 equals integral from 0 to 4 of kt 16 minus t squared dt, and this is equal to, we can bring the k out because it's a constant, and we have the integral from 0 to 4 of, we have 16t, just 16t, and then a minus t cubed dt. And what is this? This is precisely k. We have the, square brackets, integrating 16t gives us 8t squared, and then also a negative 1/4 t to the 4 using power rule, and then we go from 0 to 4. Okay, we can ignore 0 because plugging 0 in, that's going to make everything 0, which is nice. So we're just going to plug 4 into everything, What we can do as well is, instead of having to do like 4 to the 4 and so on, that's going to be messy. We can factor out a t squared, and we can do it the following way. You can write it as k, and then you can factor out a t squared, and you're left with 8 minus 1/4 t squared, and evaluate everything at t equals 4, because you don't really care about 0 over here, right? We established that. So we can plug t equals 4 into everything, and that's going to give us 16 times k, and then we have 4 over here, so that's going to be, what's 4 squared divided by 4? That's 4. So 8 minus 4, that is going to be 4. Right, so this is 64k. And because 64k, we equated that to 1 at the very start. That means that k equals 1 on 64 as required. Okay, next up we want to find e of t. Basically doing the same thing, right? We're just doing an integral. So let's integrate from 0 to 4. The form is t times the density. What's the density? It's kt, 16 minus t squared dt. And this is equal to k, integral from 0 to 4. Let's expand. So that's 16t squared minus, that's going to be t to the 4, I think. Yeah, just t to the 4, because we factored out k, dt. And let's just integrate once again. So this is equal to k, and we'll plug k equals 1 on 64 in, at the very end, just so we don't have to write 1 on 64 every single time. So this is, let's see, we have 8t, no, not 8t, because this is a squared now. So this is actually 16 on 3 t cubed. And then we have minus 1/5 t to the 5, evaluate from 0 to 4. Same idea as before. 0, we can ignore that, and we just need to plug 4 into everything. But because we're plugging stuff in, we might as well factor things to make it easier to plug in. So I'm going to choose to factor out t cubed this time, leaving us with 16 on 3 minus, and then we have a t squared that remains, right? And we evaluate all of this at t equals 4. What happens at t equals 4? We get k times t cubed. What's t cubed? It's 64. So k times 64. But remember, k is just 1 on 64. So it turns out this whole guy over here, that's exactly equal to 1. Right, so we can kind of ignore it. And yeah, we're just left with 16 on 3 minus t squared. What's t squared? It's like 16 or something, right? Yeah. And this is equal to, we have 16 on 3 minus, I think I did something wrong over here, because now we're going to get a negative number, which is not good. So let's check our working out. So 16 on 3, t cubed, that's fine. And then we have t to the 5, yes. I factor out a t cubed, leaving us with this over here. And yeah, I'm missing a 1 over 5 over here. So sometimes it's good to do these checks while you're doing your working out. Because I'm getting a negative, I was going to get a negative number, which is not good, because this density is only defined for positive values, or between 0 and 4. So we have, I was missing a 5 here, so that should have been a 16 on 5. Okay, so 16 on 3 minus 16 on 5, and that gives us a 5 times 16 minus 3 times 16 over 15, just doing a bit of cross multiplication, leaving us with 2 times 16 over 5, and that is precisely 32 over 5. Okay, so that wasn't too bad. It was just a bit annoying having to do 2 integrals, right? And we already had integrals in previous questions as well. But VCAA's not done yet, because they give us, yet again, another integral to do, because we have to calculate the probability. And this is conditional probability over here. So we want to find the probability that a person has to queue for more than 2 minutes, given they already queued for 1 minute, right? So what does that mean? It means the probability that they queue for more than 2 minutes, so t is greater than 2, given that they have already queued for 1 minute. But if they've already queued for 1 minute, that means their t value has to be greater than 1. Right, so if you just write this out over here, this is the probability that t is greater than 2 and greater than 1, which is just t greater than 2, right, over the probability that t is greater than 1. Now, when I did this the first time, what I did was I just jumped straight to the integrals, and I wrote the integral from 2 to 4 divided by the integral from 1 to 4. And this is fine, you can do this, but there's a much nicer way to evaluate it, which I found out in the middle of the working out, and I kind of scrapped the current working out in the middle. What you can do, here's the thing. Integral from 2 to 4 and integral from 1 to 4. You have to plug it into the antiderivative 4 times, pretty much, right? You have to plug those numbers in. But if you realize what we've done before, right, it's really nice to have the 0. It's really nice to start the integration at 0 because the antiderivative just vanishes. So what we can do is we can take the complements of everything over here, and instead of doing 2 to 4, we can do 1 minus the probability from, t is less than 2. Over 1 minus the probability that t is less than 1. And now these integrals are going to be integrals from 0 to 1 and 0 to 2 instead, which is much nicer, because if you plug 0 into the antiderivative, it's going to vanish, and you just need to plug in 2 numbers. Right, so let's do this. So this is probability. Let's do probability t less than 2. This is the integral from 0 to 2 of k times t. What we can do, by the way, because we're going to basically do the same integral, we might as well do the integral from t less than, I don't know, some value a, and then we can choose the value of a. All right? So this is the integral from 0 to a of kt, I think it was 16 minus t squared, if I remember this right. 16 minus t squared. So kt, and then we have 16 minus t squared. 16 minus t squared. That's not a 9, by the way. That's an a. There's some parameter a that we can plug in later. dt. We can just copy our working out from part a. This integral from 0 to a of, actually, what did we get from part a? Because we're literally going to get the same antiderivative in everything. So we're going to get 8t squared minus a quarter t to the 4. So let's just use that. So we have a k on the outside, we have an 8t squared minus a quarter t to the 4, right? And k is obviously 1 on 64. So okay, and we just got to evaluate from 0 to a, it seems like. So what does that give us? It gives us k, and then just 8a squared minus a quarter, and then a to the 4. And if you plug 0 in, it gives you 0, right? So we want the probability that t is less than 1. Let's do that first. So that just means plug in a equals 1. So this is 1 on 64. We have 8 minus 1 quarter, which is 1 on 64. 8 is precisely 32 on 4 minus 1 quarter. So that's going to be equal to 1 on 64, 31 on 4. So that's going to be 31 on 256. Right? And we can plug it in for a equals 2 as well. So probability that t is less than 2 is going to be equal to, let's say we have 1 on 64. We have 8 times 2 squared, so that's going to be 32, I believe, minus, what's 2 to the 4? It's like 16, is that right? So you just have 4 over here, I think. So this is just going to be equal to 1 on 64 times 28, so 28 over 64, both divide 4, so this is just 7 over 16. Okay, so we got our values for the probabilities there, we just gotta plug it back into the formula above. So, probability that t is greater than 2, given t is greater than 1, is equal to 1 minus. We have the probability t is less than 2, first of all, which is 7 on 16, divided by 1 minus, let's make that a better fraction, so over 1 minus 31 over 256. So evaluating this, what do we get? Well, 1 is 16 over 16, so this just simplifies to 9 on 16, I believe. So 9 on 16 divided by, again, 1 is 256 divided by 256. So if you do the subtraction, that should give you 225 over 256, right? To simplify this fraction, we can just multiply the top and the bottom by 256, leaving us with 256 times 9 on 16 divided by 225. 256 goes into, 16 goes into 256 16 times. I did the calculation in the first recording, so I kind of remembered that, but you can just probably divide it by hand if you really want to. So this is 16 times 9 over 225, and 16 times 9, I'm pretty sure that was 144 over 225. Right. I don't think you can simplify it further than this. Maybe you can, but I can't be stuffed thinking about how to divide big numbers. So I'll keep it like that. Question 9. Let's see. So this one's not too bad of a question. I was expecting a harder final question, but this one's really not that tricky at all. So we have shapes of two walking tracks. It's we have function f and function g. Function f some kind of cubic. Function g is a nice quadratic, and we're given some values that these graphs must pass through, and we want to verify some numbers. So they really made it easy for us. So let's say f of 0 is 12, which means 12 is equal to f of 0, which means plugging 0 into there, which is a minus 0, 0 minus 2 squared, but that's just a, because 0 times everything is 0. So that means that a is equal to 12. Nice. And then let's do the same for the value of b. So we know that g of 1 is 9. So 9 is equal to g of 1. What's g of 1? Well, it's 12 minus b. No, plus b. 12 plus b, which means b is equal to negative 3. So we've got those two values there, nice and simple. So part b, I think this was the turning point question. So we want to find, verify that f and g both have a turning point at p. Give the coordinates of p. So let's write down the functions f and g. So we know f of x, this was our cubic friends. I think it was 12 minus x minus 2 squared, was it? Let's check, because a was 12. So 12 minus x minus 2 squared, indeed. And g is just 12x plus a bx squared. B is negative 3, so that's going to be 12x minus 3x squared. So we have f of x over here, and we have a g of x. G of x is going to be equal to, we have 12x minus 3x squared. We want to differentiate both of these, and set it equal to 0. So that shouldn't be too bad to do. I'm going to rewrite f so we can actually differentiate it. So this is 12 minus x, and then x minus 2 squared. What's that going to be? That's x squared minus 4x, and then plus 4. So let's see. We have a 12 minus x cubed plus 4x squared, and then minus 4x. Okay, so that's our function f. So let's calculate f prime of x. So f prime of x is going to be, 12 disappears, so we're going to be left with negative 3x squared plus 8x, and then we have minus 4. Okay, and let's calculate the g prime of x as well. So g prime of x is going to be, that's nice and simple, just 12 minus 6x it seems like. And we want to set both of these equal to 0. Let's do that. So that's g prime of x equals 0. Let's do that first of all, because it's simple. So that means 12 minus 6x equals 0, which means that x is just equal to 2. Okay, that's the only solution, which means we kind of want f to have the same solution as well, or f prime equals 0 to have the same solution. So what we can do is we can just plug 2 into f prime and make sure that's equal to 0. So that's negative 3 times 4, and then plus 8 times 2, and then minus 4, and that's equal to negative 12 plus 16 minus 4, and yeah, that should be 0. So 0 is a stationary point of f. We can argue that over here it's a turning point of g, because g is a quadratic, which means that all stationary points are turning points, so TPs. We don't really know that about the cubic, because what if it has like a point of inflection, a stationary point of inflection? We got to check that. So how do we check that? We can use a sign diagram for the derivative. So we know at 2 it's going to be 0. Let's do a sign diagram over here. So x, f prime of x. Let's do 1, 2, 3. So 2 is in the middle, derivative is 0, so it's going to be horizontal line. Let's plug in 1 into the derivative of f, and that's going to give us negative 3 plus 8 minus 4, which is 1, I think. So yeah, we're going to get a positive gradient here. If you plug 3 into the derivative of f, you're going to get negative 27 plus 24 minus 4. And if you work that out, I think that's like negative 7, because you've got negative 3 minus 4, which is negative 7. So negative, so you're going to have, local max. So on the cubic, we can verify that it is indeed a turning point as well. Okay, part C, final question. We have a theme park. We have the boundaries form a triangle OAB. So it's a triangle down here. And what we want to do is find the maximum possible area of this triangle in terms of k. Right, so this area is in terms of k. We want to find the value of k which maximizes the area. That's what we want to do. So let's try to find a of k. So the area of k is just equal to 1/2 times base times height. What's the base of this triangle? Well, it has to be k, right? Because the point A has coordinates k, 0. So this is 1/2 times k. What's the height? Well, it's just the y coordinate of b, but y coordinate of b is just a g of k. So yeah, it's just 1/2 of k times g of k. And this is equal to 1/2 k. What's g of k? Was it like 12k minus 3k squared? Let me just check that. So it's 12. I know it's 12. Is it 3k squared? I think it is, because b was -3. Yeah, 12x plus bx squared, or 12x minus 3x squared. So if you plug k in, that's what you get. And let's expand this because we need to differentiate. So this is, let's see, we have a 6k squared. And then we have a minus 3 on 2k squared, or k cubed rather. And differentiating, we get a prime of k is equal to 12k minus, we have 9 on 2k squared. Right, and we need to set this guy equal to 0. And setting it equal to 0, what do we get? We get, let's see, we can multiply everything by 2, which gives us 24 minus 9, 24k minus 9k squared equals 0. And you can factor out a k, so 24 minus 9k is equal to 0. But remember over here, k can't be equal to 0 because k is on the interval 0 to 4, non-inclusive. And if k was equal to 0, you're just smashing this triangle down to a singular point. So obviously it's going to be one of those, yeah, your local minimum there. So it's not k equals 0. So it has to be, yeah, you have to solve the other factor equals to 0. Let's do it all the way up over here. So 24 minus 9k equals 0, which tells you in the very end that k is equal to 24 on 9. I think that was all we needed to do. Did we need to find the area as well? Hopefully not. Find the maximum. We did need to find the area. So that was the value of k for which it occurs. Find the maximum possible area of the theme park. So we need to plug this k value back into the area. How do we do that? It's a good thing I'm doing this again because I think in my original recording I just stopped over here and I didn't plug it back into the area. So what's the area going to be? It's going to be, oh dear, they really didn't give us enough space, or maybe my working out just really inefficient. I don't know. Let's just do it. Let's just do it on the side here. Why not? So let's see. We want to evaluate a of 24 and 9. So I'm going to use, I think this expression for the area wouldn't be too bad to use. Let's do that. So we have 1/2. We have k, so 24 on 9. And then we have a multiplied by 12k. So we have 12 times 24 on 9. Minus 3 times k squared, was it? 3k squared. Yeah, 3k squared, so that's going to be 3. Then 24 over 9. But this thing is squared. That is absolutely gross. So how can we simplify this? This is 12 over 9. What's 12 over 9? That's like 4 over 3, I think. So we have 4 over 3. And then we have another 12 over 9 situation over here, so that's another 4 over 3 times 24. But 3 and 4 will cancel. 3 and 24 will cancel, giving us 8. So that's really 4 times 8, which is 32. So 32 minus, we have, oh dear, we have 3 times 3 over 9 squared. So that's 3 over 81, is it? Let's write it like this. So 9 times 3 times 3. That's 9 squared for you. But one of these 3's will cancel, leaving us with 1 over 27. So this is 1 over 27. And then 24 squared. That's interesting. Dear. So this is going to be equal to 4 on 3. 32 minus 1 over. I'm going to write this as 3 times 9. I'm going to write 24 as 3 times 8. And then times 3 times 8 once again. Sometimes it's nice to decompose your big numbers into factors, so it makes it easier to simplify. So this is 4 and 3, 32. A 3 and a 3 will cancel, and this is going to leave you with, yeah, another 9 and a 3 over here can cancel as well, which is quite nice. So really, I should have written that 27 down there. I really should have written that 27 as 3 times 3 times 3. So that's 3 will cancel, 3 will cancel, leaving you with 64 over 3. Okay, so we have minus 64 over 3. And let's see. We probably want to get 32 on the same denominator as well. So this is 4 over 3. What's 32 times 3? It's 96, I think. So 96 over 3 minus 64 on 3. And what's 96 minus 64? 96 minus 64 is 32, I think. So this is 32 over 3. So this is going to give you, is it 32 on 3? I think it's, yeah, it's 32 on 3. That's going to give you 128 over 9. That's the final answer. I spent like 10 minutes on that, probably doing that arithmetic. But yeah, I hated how they put arithmetic, like this level of arithmetic into the exam. It's just, yeah, it's just annoying. Like instead of giving us hard arithmetic problems, give us like an actual hard theoretical type of question. I'd enjoy that a lot better. I don't know about you guys though. I don't know if you guys like doing this sort of arithmetic. But yeah, reminds me of the 2021 because you got like a whole pile of arithmetic and you also got like these integrations as well. And there's a lot of integrals in this exam though, which is surprising. I've never seen an exam with this many integrals. But yeah, overall, I think it's a fairly fair exam. I mean, I'm at like 40 something minutes already. To be fair, I took a bit longer on my first round because I also had to think about the questions a little bit as well. So yeah, a lot of people said they were tight on time, which is, yeah, very fair because I'm already, yeah, there's only 10 minutes left until like the 1 hour is over. But yeah, I think the probability, I really don't like how they just spammed us with a whole lot of integrals over here, especially parts C over here. I didn't like that at all. The other parts, I liked the confidence interval question. That was a nice and neat question. And yeah, everything else was pretty standard. Nothing too special for the first few pages. But yeah, that's the new study design for you. And yeah, that's pretty much all for this video. So hopefully you guys enjoyed. Hopefully I get my hands on the exam 2 as well when it comes out tomorrow. Yeah, if you have questions, leave them in the comments below. And yeah, if you're watching this today, then good luck for exam 2. And if you're a special student, good luck for your exam 1 and exam 2 on Friday and Monday as well. That's all from me. And yeah, see you in the next one.